that these three experiments could be best explained by introducing the photon or particle nature of light, and hence introducing the nature of quantum mechanics. But it's not just about particles with quantum mechanics. Some experiments are best explained by this photon model. Some are best explained by a wave model. We must accept both models and admit that the true nature of light is not describable in any single classical model, but in terms of either of these models. Also, this particle model and the wave model of light complement each other. They show different properties of lights that we know to be true. Along comes Louis de Broglie, 1892 to 1987. I guess he was 95 years old when he died, so that kind of shows that doing physics can be good for your health. French physicist, originally studied history, awarded the Nobel Prize in 1929 for his prediction of the wave nature of electrons, in other words, matter waves. Was a member of the Marx Brothers. Here are the Marx Brothers, a famous comedy trio from the early 1900s. Did a lot of movies, really funny. You have Harpo, Chico, and Groucho, extremely funny. Little known that there was a fourth Marx brother. His name was Carl, and he was always talking about the oppression of the people, the power of the proletariat. He wasn't that very, very funny at all. And so eventually they got rid of him, and they added Louis de Broglie. Because when Louis de Broglie wore Chico's hat, he looked a lot like Chico. So it looked like they were brothers as well. Most of what I tell you is true. That wasn't true. But the idea of matter waves, of matter acting like a wave, well, that probably was pretty funny in that day and age. De Broglie thought that if the photons have both wave and particle characteristics, perhaps all forms of matter have both wave and particle characteristics. He defined the de Broglie wavelength of a particle as being equal to Planck's constant divided by the momentum of the particle, or h divided by mv. And in analogy with photons, the de Broglie frequency would be equal to the energy of the particle divided by Planck's constant. These equations represent the dual nature of matter. Particle nature is expressed in terms of momentum and energy, and the wave nature is expressed in terms of wavelength and frequency. In calculating a de Broglie wavelength, it is often useful to relate the kinetic energy to terms of its momentum in a non-relativistic sense. So energy is equal to 1/2 mv squared, but we know momentum is mass times velocity, so we can write this as 1/2 mass times velocity squared over mass, or 1/2 the momentum squared divided by the mass. And if we were to go the other way around and express momentum in terms of energy, we could reverse this and say that momentum is equal to the square root of 2 times the mass times the energy. Well, if this theory were true, if particles do have a wave nature, then maybe as a wave they should express or exhibit wave properties, things like diffraction. Diffraction is truly a wave effect. And so if particles could exhibit diffraction, they are acting like a wave. Davidson and Germer observed electron diffraction, and hence they were able to measure the wavelength of electrons and prove de Broglie's theory about matter waves, that matter acted both as a particle and as a wave. Here's how it might look. Monoenergetic beams of electrons are incident on a double slit. The slit widths are small compared to the actual calculated electron wavelength according to de Broglie's formula. As the electrons encounter this double slit, we see a diffraction pattern appear on a screen. Looks something like this. If you threw 28 electrons at the double slit, you might get this pattern that looks like this. You really can't see much organization to where the dots are falling. But after 1,000 electrons, you start seeing some maxima and minima. And after 10,000 electrons, definitely you see bands of maximum and minima in this pattern, just like diffraction. There's distinct evidence that electrons are interfering like a wave-like behavior. As you do more and more and more, you get a diffraction pattern that definitely looks like a light diffraction pattern or a wave-like diffraction pattern. So, what is electron diffraction? With this double slit experiment and the wavelength of the electron being larger than the slit width, an electron actually interacts with both slits simultaneously. If you try to determine which slit the electron went through, the act of trying to measure the interference pattern would break the wave function, and hence you would not be able to determine exactly which slit it went through. In other words, really truly maintain the wave aspect of the electron, it really goes through both slits in a probability sense. Part of it goes through one slit, part of it goes through the other slit as it acts like a wave. So, in essence, J.J. Thomson was responsible for determining or discovering the electron and determining it to be a particle. He won the Nobel Prize in 1906 for saying the electron is a particle. His son, independently with Davison and Germer, George Paget Thomson, also showed that electrons could exhibit diffraction, and he jointly won the Nobel Prize with Davison and Germer in 1937, basically for showing that the electron is a wave. So we have the wave-particle duality here all in one family. Here's a setup of the electron microscope, which is using this property of waves in order to find a more defining microscope, or being able to look at things with much better resolution. It relies on the wave characteristics of electrons, shooting an electron beam, focusing it onto a specimen, and then you have the scattered electrons according to diffraction, and you can pick up those and also your main beam. Since the electron wavelength is much shorter than light, the resolution is much better than light, typically 1,000 times better than visible light, allowing you to see much smaller objects. The specimens for electron diffraction are sputter-coated with gold, allowing them to carry away excess electrons so you don't have that interference. And so actually in themselves, the specimens look pretty neat. Here's a electron diffraction, electron microscope picture of an ant, I guess. Pollen. Not sure what that is. I think that's the head of a flea. And I'm not sure what that is, but I wouldn't want to come up against it in a room. It's pretty alien. Werner Heisenberg, 1901-1976, German physicist, developed matrix mechanics. Many contributions to science include the uncertainty principle, the prediction of two forms of molecular hydrogen, and the theoretical models of the nucleus itself. Received the Nobel Prize in 1932, was in charge of Germany's nuclear bomb program in World War II. He was in charge of the program before World War II, and this is actually going to be a true story I'm going to tell you. The Allies sent a possible assassin to one of his talks that he held outside of Germany prior to the war. I think it was prior to the main war in 1939. And the assassin's his instructions were to assassinate Heisenberg if, in the course of his talk, he said anything about nuclear bomb or nuclear program. Of course, he didn't say anything about that in his talk. And as the story goes, the assassin actually waited until the talk was over and confronted Heisenberg in the street as he was walking along on his way home. And it was, again, tried to pinpoint him on what his stand was on nuclear bombs, and Heisenberg just kind of shrugged him off and kept on walking. Kind of an interesting story. The assassin had never actually ever killed somebody before, and possibly, in this sense, he probably should have gone ahead and done it, because if Germany had gotten the nuclear bomb first, it would have been a disaster for the world. For his credit, after the war, Heisenberg said that he personally tried to sabotage Germany's efforts to make a nuclear bomb. Even though he was in charge of the program, he tried to make sure that it was never successful. At least that's what he said after the war. During the war, though, it was increasingly evident that the Allies would want to find him. So they were looking around for him. But everywhere they looked, or tried to look, he never seemed to be there. They tried and tried to find Heisenberg, but he always seemed to escape their observation. This is called the Heisenberg uncertainty principle. No, I'm just joshing you. The true introduction to the uncertainty principle goes like this. In classical mechanics, it is possible in principle to make measurements with arbitrarily small uncertainty. In other words, infinite accuracy. You can measure something totally as accurate as possible. In quantum mechanics, nope. Quantum theory predicts that it's fundamentally impossible to make simultaneous measurements of a particle's position and momentum with infinite accuracy. It's not a problem with measuring. It is a problem inherent with the wave nature of matter, the probability of matter being in one place and another place at the same time. If a measurement of the position of a particle is made with uncertainty delta x, and a simultaneous measurement of its x component of momentum is made with uncertainty delta p sub x, then the Heisenberg uncertainty principle is uncertainty delta x times uncertainty delta p sub x is greater than or equal to a constant h bar divided by 2. When Heisenberg first introduced this, he had it as greater than or approximately equal to h bar, but more experiments, more studies in different forms of quantum mechanics finally nailed down this uncertainty relationship as being greater than or equal to h bar divided by 2. H bar is the reduced Planck's constant. It is h divided by 2 pi, which is 1.055 times 10 to the minus 34 joule seconds. Oftentimes in problem calculations, the 1/2 is again dropped, somehow lost. And I think in the problem calculations you'll have in your problem sets, be ready for that. So oftentimes it'll be expressed delta x, delta p sub x as greater than or equal to just h bar. So be ready for that. Not sure why, but be ready. It is physically impossible to measure simultaneously the exact position and the exact momentum of a particle. This does not result due to imperfections in practical measuring instruments. In other words, if you made the instruments better and better and better, would you be able to forego the Heisenberg uncertainty principle? And the answer is no. It is a basic, intrinsic result of quantum mechanics. So it really depends on the quantum structure of matter, the probability, the idea that things, even like electrons, act like waves. Another form of the uncertainty principle can be expressed in terms of energy and time, and it looks like this. The uncertainty in energy times the uncertainty in time is greater than or equal to h bar divided by 2. So there's always a minimum limit to that. One interesting aspect of this form of the uncertainty principle is that it suggests that energy conservation can appear to be violated for a very short period of time. If you had a short period of time, you might be able to get energy to go to change above some maximum limit with your delta E with some uncertainty if your time is short enough. Kind of an interesting result, and becomes important in some aspects of quantum mechanics. Say if you had a wave encountering a barrier, it possibly can tunnel through that barrier, actually exceed the energy of that barrier for a short period of time, so it can find itself making it to the other side. And this is indeed what happens in electronic systems. In using this formula, again, oftentimes when you're doing problems, you will drop to 1/2 and it will simply just be greater than or equal to h bar, or 1.055 times 10 to the minus 34. That concludes the second lecture of chapter